Now that you know the basics of how simple harmonic motion works, I want to talk a little bit about some of the energy considerations here. First, I'm going to remind you that the position and velocity as a function of time can be expressed as sines and cosines as shown there. Now, I know there are other ways of doing it, but let's just stick with the sine and cosine, and you'll see that if I chose to do a position as a cosine function and velocity as the negative sign, it would still work out the same. For now, I've got position as a sine omega t plus theta naught, and the velocity is the derivative of that, omega times a cosine omega t plus theta naught. Well, let me just, for giggles here, I'm going to point out that what this means is the maximum position that I will have, x max, is a, which makes sense. That's what the amplitude is after all. And the maximum velocity I will have is where that function gets maxed out, where the cosine goes to 1, and that's omega times a. So V max equals omega times a. And I'm going to square both these guys. I'm going to take x and make it x squared, and take v and make it v squared. And my reason for doing this is because x squared is related to the potential energy of the elastic force, and the k, the kinetic energy, goes as v squared. So if I look at the elastic potential energy, 1/2 kx squared, what I see in this case is it's 1/2 ka squared sine squared omega t plus theta naught. And the kinetic energy at any given time is 1/2 m omega squared a squared cosine squared omega t plus theta naught. Now, you probably don't have in your head right now what the sine squared and cosine squared look like. So we're going to walk through this just to make sure we understand it a little better. First, though, I want to point out that kinetic energy really is 1/2 mv max squared times cosine squared. So if I look at it, u peaks out when the sine is equal to 1. The largest value of u is 1/2 ka squared, which makes sense. That's when the spring has stretched the most at x max. And the kinetic energy is largest when the cosine goes to 1, when 1/2 mv max squared is the kinetic energy. Anything less is going to decrease the kinetic energy, and anything off sine equals 1 is going to decrease the potential energy. So let's walk through it and see what this looks like. Top graph shows you the position as a function of time for a simple harmonic oscillator, and I've just chosen k equals 2 and m equals 2 to make it easy if you really want to check this plot. What that does is that means that 1/2 ka squared is going to be 1. It's going to give me an amplitude of 1 on this oscillator, and the maximum velocity is also going to be equal to 1. Well, if I look at the potential energy, this is the elastic stretch energy, the 1/2 kx squared. That's what the plot looks like down there at the bottom. That's a sine squared plot that you're seeing there. And notice that it peaks up to its maximum value when the sine function is at its top or at its bottom of its oscillation. The kinetic energy, on the other hand, is shown by this blue curve. It's going to peak when the velocity is largest, which actually is when it crosses through the origin again. So it's a cosine squared curve, and it is a little out of sync with the sine squared curve. In fact, it is exactly out of sync with it. So that what we see happening here is I'm just swapping energy between the kinetic and the potential. As the blue curve goes down, the gold curve comes up, and vice versa. And if I were to add both those together, I would find that they're always equal to 1. The kinetic energy plus the potential energy always adds up to be the total energy, of course. And what I've got is the total energy is conserved, and it's just alternating back and forth between kinetic and potential at twice the rate of the thing that's oscillating by itself. Also notice that the total energy can be found by 1/2 ka squared or 1/2 mv max squared. It can either be the total potential energy or the total kinetic energy, because either way, that's what the energy maxes out to.